Welcome back. In our last video, we derived nested logit probabilities and showed that they can be broken down into a factorized form, where one component is the choice of nest and the other component is the choice of alternative within nest. In this video, we'll talk about how to estimate the parameters of the nested logit model. And the key insight is that factorization of the probabilities that we talked about in the last video can simplify the process of estimating the parameters by breaking it into manageable chunks. We can estimate some parameters using only the alternatives in a particular nest, and we can estimate other parameters using the different top-level nests. This sequential estimation approach offers computational advantages, but it's not the only way to do it. We can also use all of the nests simultaneously in what's called a full information maximum likelihood, or FIML, approach. We'll conclude the video by talking about the pros and cons of each type of estimation approach. The log likelihood for the nested logit model can be written in the same way as the multinomial logit model. The only difference is that the form of the choice probabilities is different. And one advantage of the nested logit model is that we can break down this summation across alternatives into the different nests. So I have the car alternative as one option from this summation over J, and then I have another component that is the summation over alternatives within the bus nest. So the J sub B here means the maximum alternative or the set of alternatives that's in the bus nest. And we can expand this further and distribute the log through to these different probabilities, and then we get a nice additively separable likelihood function that has different probabilities in each component. And the key idea here is that PB is the probability of choosing any bus, and then PJ given B is the probability of choosing a particular bus given that a bus was chosen. So these are all equivalent, mainly due to rules of multiplying probabilities together and conditioning on probability and conditioning probabilities on different events. We can further expand the equation from the previous slide by noting that depending on whichever bus you choose, you're going to get the same log of P of bus in this middle component. And so then we have just this summation over the individual bus alternatives in the last component. And the key insight is that with this additively separable log likelihood function, we can estimate the different components separately and still get consistent parameter estimates. They won't necessarily be efficient in the sense that the estimator would have the minimum variance, but they will give you consistent estimates. So now, to pursue this sequential estimation idea further, let's decompose the utility for the red bus as having a component that's the utility for writing any bus, and then a separate component that's the utility of writing a red bus given that a bus was chosen. Then we can make some other normalizations. We can normalize the utility of the car to be 0 and the utility of blue bus given bus to be 0. And if we make those normalizations, then what are the parameters we're going to estimate? We're going to estimate a beta associated with any bus. We're going to estimate a beta associated with a red bus, and then some alternative specific variable coefficient gamma, and then the nesting parameter lambda. So these are the 4 parameters that we're estimating. If we impose the normalizations that I just said, the utility of a car is going to be 0. Utility of blue bus is just going to be the bus utility plus gamma times whatever the difference is between the blue bus and the car in this Z characteristic. And then the utility of the red bus is going to have this blue bus, but then adding the red bus component for the betas times X. And then we're going to have the red bus specific characteristic, and that's going to have the same coefficient gamma. So in stage 1 of this estimation, we're only going to use the observations that chose bus. And basically, this is just a binary logit with the red bus and the blue bus. And the blue bus was normalized to 0. So that's where this log of 1 plus exp is coming from. So this is literally just a binary logit using only the observations that chose a bus. Now, to link this with the second stage, we need to define a concept called the inclusive value. And this is just the denominator of the within bus nest probability. So this second term here, which is the log of the denominator of the probability within the bus nest, we're going to call that the inclusive value. And then we can rewrite the nest probability very succinctly. So if you remember from a prior video, we had this sum of exponentiated utilities raised to the lambda power, and then each utility was divided by lambda. So this simplifies down to exp of the blue bus utility plus this inclusive value. And lambda times the inclusive value is going to give you the expected utility associated with the bus nest. And if you remember, that's a review from a prior video where we talked about expected utility, and that the log of the sum of the exponentiated utilities is the expression for the expected utility, given that you're going to choose the maximum of those utilities as your choice, the Emax. So now that we have that inclusive value, we can link it in stage 2 to estimate the bus parameter. We're using all of the observations now, and if a bus was chosen, we're going to hit it with this utility of the blue bus plus the lambda times inclusive value. And then in the denominator, we're just going to have the same component here in the numerator, but then add 1 and then take the log. So the 1 here is the utility of the car that was normalized to 0. And then we're getting the inclusive value number from the stage 1 estimation. So the stage 1 estimation is giving us this inclusive value term that we can then use in stage 2 to tell us something about the relative attractiveness of the bus relative to the car. And the reason the inclusive value has this nice interpretation is because you can think of it as the expected utility of choosing the bus. So it has some flavor of option value in that sense. And again, this sequential estimation works because we have an additively separable likelihood. So the stage 2 likelihood, we're recovering estimates for the red bus and the gamma. And then given those estimates, we plug those into the first stage log likelihood, and then we can estimate the parameters of the bus and the nesting parameter lambda. So the parameters beta, RB, and gamma, they're only identified from within nest variation, and so that's why we're able to separate them out in this way. And then we take them as given when we're doing the stage 2 estimation to get the between nest parameter estimates. Now, a separate option is to just do everything in one shot, don't do these different stages, and estimate all the parameters simultaneously. So again, in this case, we could have the same log likelihood function. We're just going to have a different formulation of these choice probabilities, and we're going to use the same factorization that we talked about in the prior video, where we have a probability of choosing the nest and then a probability of choosing the option within the nest. And the product of those is just going to be the individual alternative choice probability. So this is a recreation of the formula from the prior video that shows this factorization. We're going to plug in these for every single alternative in our choice set, and then we can just plug that into the likelihood and directly maximize. So what's the advantage of doing it all at once? Well, efficiency is a big advantage. So we're going to get lower standard errors around our parameter estimates if we estimate them all in one. And we're also going to get the correct standard errors because we're incorporating both steps simultaneously. If we do the multi-stage approach, we might get standard errors that are wrong because they don't take into account the estimation uncertainty from the previous stage in the second stage. If we can get the, if we use FIML, we can also test hypotheses that are going across the stages of the estimation. Another way of saying that is that we can recover the variance covariance matrix for parameters that enter different stages. Whereas if we do them stage by stage, then we won't be able to get that covariance unless we do something like bootstrapping. What are the disadvantages of this full information maximum likelihood approach? It's computationally more demanding. It may have less stable convergence, especially if you have a boundary value for lambda. So if lambda is very close to 0 or 1, and it requires good starting values. Some other things to just keep in mind when estimating a nested logit model. The log likelihood function is not globally concave, which means that depending on the starting values that you give it, you might get different estimates. It's also the case that in some formulations of the nested logit, you might have the same parameter entering two different stages. And in that case, you might get two different answers for those parameters, and then you'll have to figure out how to reconcile those differences. So what FIML is going to do is it's going to enforce that parameter be the same value regardless of which stage it enters. Another thing to keep in mind with any nested logit model is that you have to find a lambda that is within the unit interval. Otherwise, your model is not consistent with utility maximization. So that's how we estimate the nested logit model. The key idea here is that the factorization of the different nested probabilities allows us to estimate the parameters sequentially, but we can also choose to estimate them simultaneously, and there are pluses and minuses to each approach. In the next video, we're going to explore how nested logit models have a dynamic interpretation that I briefly alluded to in this video. And in particular, we'll see how the inclusive value represents the future utility, the expectation of the future utility that one might get from making a particular choice. And this has an analogy to a dynamic scenario where tomorrow's unobservable preferences may not be known to the individual when making their choice today. So I hope to see you in the next video.